In this video, we're going to be illustrating the normal distribution through an example from quality control. And the objective is to show how to use the normal distribution in the normal table in a couple of different ways. So the setting is as follows. A manufacturing company produces plastic cylinders. The specifications for the cylinder state that it should have a diameter of 5 centimeters. A deviation of more than 0.02 centimeters from this target is considered a defect. The process used to manufacture the parts exhibits variability described by a normal distribution. So the normal distribution I've drawn here shows the diameters, the distribution of diameters of parts actually produced. So the mean is 5, but there's some dispersion around the mean, and that dispersion is described by a standard deviation of 0.009 centimeters. Remember that the specifications allow a tolerance of 0.02 centimeters plus or minus, and so the shaded area here shows the parts that are good. We want to know what proportion of parts conform to specifications. Okay. Well, the way we want to think about this, as with pretty much all normal distribution problems, is we want to think of this distance here, which is 0.02 centimeters. We want to convert that into the number of standard deviations. So when we take the difference between these two numbers, that's the difference in centimeters. When we divide by the standard deviation, that gives us the distance measured in standard deviations. This distance is plus or minus 2.22 standard deviations away from the mean. So our objective is to find what fraction of a normal distribution lies within plus or minus 2.22 standard deviations above the mean. The approach we'll take is to find the proportion of parts that are too large. That's going to be the unshaded region here, and the proportion that are too low. Right, well, we found that this is 2.22 standard deviations above the mean. We need to know what fraction of parts are below that, so we need to know what fraction of the normal distribution is below 2.22. So we go over to the normal table and we look at 2.22. Last column gives us the last digit, so 2.22 gets us to 0.9868. And that's what I've indicated here. The shaded region corresponds to 98.68% of the normal distribution, and therefore 1 minus that corresponds to 1.32%. So in terms of our original setting, that means that 1.32% of parts produced are going to be too big. They're going to be in this upper region. By symmetry, 1.32% of parts are also going to be too small. Remember that our tolerances were symmetric about the mean. 1.32% is the fraction of the normal distribution that's more than 2.22 standard deviations below the mean. Okay, so the total proportion of defects is twice the fraction that are too small. So it's the fraction that are too big plus the fraction that are too small. That's 2 times 0.0132, which gives us 2.64%, which means that the proportion of parts that conform, that's the middle region here, proportion of parts that conform is given by 1 minus the proportion of parts that are too large. That leaves us with 0.9736. So 97.36% of parts are good. 97.36% of a normal distribution lies within plus or minus 2.22 standard deviations of the mean. Let's look at a different problem now, lowering the defect rate. By investing in better technology and improving its manufacturing processes, the company can reduce the standard deviation of parts produced. So by reducing the standard deviation, it's going to have more parts conforming to specifications. How small does the standard deviation need to be so that 99% of parts produced conform to specifications? Remember that under the previous standard deviation, only about 97% of parts were conforming. We want to get that up to 99% of parts. We're going to need a smaller standard deviation. All right, so our goal is going to be to find the standard deviation sigma that makes a full 99% of parts fall within this region of plus or minus 0.02 centimeters. Okay, which means we want to think about now how many standard deviations apart does that need to be if we're going to capture 99% of the distribution. Well, if we go to the normal table, we want to find the z-value that's going to give us 99% of the distribution in the middle. We're going to split the remaining 1% evenly on either side, so we're going to put 0.005 in the upper tail. which means we need 99.5% to be below this level. So we're going to go to the normal table, and now we're looking in the inside of the table rather than the outside, and we're looking for 99.5% of the distribution, and we get to it right about there at 9951, and that corresponds to 2.58. So 2.58 gives us 99.5% of the distribution. Okay, and that's why I've got 2.58 there. So under any normal distribution, 99% lies within plus or minus 2.58, which means that we need 5.02 centimeters to be 2.58 standard deviations above 5 centimeters. What does the standard deviation need to be to make that true? Well, we need 5.02 minus 5 divided by 2.58. That's the magnitude of the standard deviation. That's going to put 5.02 exactly 2.58 standard deviations above 5. That's what this equation is saying. So we need to shrink the standard deviation down to 0.0078. Before it was at 0.009, and only about 97% of the distribution was within tolerance. Now by shrinking the standard deviation, we've got a full 99% lying within plus or minus 0.02 centimeters of the mean.